we have a group G, and let us consider a of subgroup of G, say H, right? And then using this subgroup, we have defined a relation on G such that for A comma B belongs to G, A is congruent to B modulo H if and only if A inverse B belongs to H, right? And we have proved that this relation is an equivalence relation, right? Is an equivalence relation defined on G, and which determines equivalence classes that are called left cosets of H in G, defined by an element defined by elements of the group, right? Elements of G, that is, for every A belongs to G, we denote the left coset of H in G as AH. And in the additive group, we designate this as A plus H. Okay, A plus H, since the operation concerned in the group is addition. So that is why we are designating this left coset in an additive group as A plus H. And recall that every equivalence relation on a set defines a partition with respect to this relation in terms of distinct equivalence classes, right? And therefore, with respect to this observation, therefore, the given group G can be decomposed into distinct left cosets of H in G. That is, G is union of small a h, where small a belongs to capital A, where this capital A denotes the set of all representatives taken from each distinct left cosets, left coset of H in G. That is, we are just taking out the representative from each distinct left coset of H in G, and uh, then take the union of those left cosets, distinct left cosets, and that will be the whole group G. And for that reason, this decomposition is called so yeah. So this decomposition is called the left coset decomposition of the group G. Okay, right? Fine. Now, in the same way, using the same techniques and same ideas, we can define another equivalence relation out of that subgroup H in the group G. But what is the relation? The relation comes from the fact that the criteria of a subset in a group to be a subgroup. What was the criteria? The first one was H is a subgroup of G if and only if for AB belongs to H, A inverse B belongs to H. That was the first criteria. And in a similar way, you can also say that there is another, that H is a subgroup of G if and only if for A comma B belongs to H, AB inverse belongs to H, right? So in the first equivalence relation, we have used this notion. Okay, we have used this notion, and now we are going to move to this one. Okay, so now let us define another equivalence, another relation. Okay, I can say that another equivalence relation on G with respect to the subgroup H by, what is the relation? For A comma B belongs to G, A is congruent to B modulo H if and only if A B inverse belongs to H. Okay, right? And in a similar manner as in the above, as in the previous case, you can you can prove that this relation is going to be an equivalence relation on the group G with respect to the subgroup H. And since it will form an equivalence relation on G, then you are going to have equivalence classes. And what are those? So let us have a look on the equivalence classes. So now for any A belongs to G, the equivalence class of A is, let us generally denote it by class A. So it will contain all those B belongs to G such that A is congruent to B or B is congruent to A mod H, right? Since the relation is an equivalence relation, so it is in particular symmetric. So you can use that fact. So this class A will contain all those B belongs to G which are congruent to A mod H, right? So that means that all those B belongs to G such that B A inverse belongs to H. That is the fact that gives you small h belongs to capital H, with respect to which you can write down BA inverse as H, or some small h belongs to capital H, right? So that means it contains all those G belongs to capital G which takes the form HA, right? For H belongs to capital H. So in general, which elements does it include? The elements which are of the form which are of the form HA, where H belongs to capital H. And this class will be denoted by HA. And it is called the right coset of H in G, determined by small a, right? And for an additive group, we shall designate it as H plus A. Okay. And since these are the equivalence classes, so we all know that any two equivalence classes are either distinct or they are identical. Either they are disjoint or they are identical. So distinct cosets, right cosets are disjoint, right? So in a similar way, we can make a note that any two right cosets of H in G are either identical, either they are equal, or they are disjoint, or they are disjoint. That is, distinct right cosets of H in G are disjoint. Okay. And in view of this, G can be decomposed in terms of right cosets of H in G. That is, G is union HA. A belongs to capital A dashed, where A dashed is the set of all representatives taken from each distinct right cosets of H in G. And this decomposition will be defined to be the right coset decomposition of the group G with respect to H. Okay. So you can decompose the group G in terms of left cosets and right cosets. The first one will be called the left coset decomposition of a group, and the second one will be called right coset decomposition of a group. Okay, fine. Okay, okay. Now, some note. Number one, that let G be a group and H be a subgroup of G. Okay, then 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 any left coset, or you may take right cosets also, any left coset or right coset of H in G is equipotent with H. That is, the cardinality of a left coset or a right coset coincides with the cardinality of H. Okay. Why it is so? Because suppose that H be a left coset of H in G. Okay. Uh, Okay. So yeah. So suppose that AH be a left coset of H in G, then define a map phi colon H to H. Uh, what would you like to show? We are going to show that there exists a bijection in between AH and H. And in view of this, you can say that H and AH have the same cardinality. That is, they are equipotent. They have the same number of elements. Okay, fine. So by the rule, so then define a map phi colon H to H by phi of small h equals to H. Okay, right? Then phi of H1 equals to phi of H2 gives you that AH1 equal to AH2, right? Now, since it is a group, it is in the group. So by cancellation law, so by LCL, H1 equal to H2. That means phi is 1, 1, right? Also, for any AH belongs to capital as AH, the coset AH, we have this H belongs to capital H, thus that phi of H equals to H. And so this implies, so by definition, phi is onto. We do not need to ensure that phi is onto because it is by definition. Okay, so it is trivial that phi is onto. So phi, so this shows that phi is a bijection. Fine, from H onto H. That is, this proves that the cardinality of H equals to the cardinality of H. And not only that, if you consider right cosets, then also it is true. And the proof is similar to this one. Okay. And in this way, since the relation of being cardinal, the relation of being same cardinality in the collection of sets is an equivalence relation, right? That means in particular it is transitive. So if you take any left coset, okay, if you take any left coset, if you take any two left cosets, suppose if you take AH, BH. Now using this one, you can say that they have the same cardinality. Now since the relation of being same cardinality is an equivalence relation, so in particular it is transitive. So that means cardinality of H equals cardinality of BH. That is, any two left cosets or any two right cosets have the same number of elements. Okay, right? And in the same way, using the same fact, same idea, you can also say that uh, any left coset H is equipotent with a right coset, right? Because these are all same. cardinality of HA, cardinality of HB, and these are all same. It equals with the cardinality of H. So that means any left coset, and if you consider any right coset, then they have the same cardinality also. That is an interesting fact actually. Okay, so this thing can be recorded as, so suppose, let G be a group and H be a subgroup of G, then for any small a belongs to H, small a comma b belongs to H, the cosets H, H, BH, HA, HB are all equipotent with each other, or you can say that equipotent with H. Okay, okay, so that thing I do not need to write, because I have already considered H, so this is fine. Okay, okay. And another interesting fact is that not only that, that any two left cosets are equipotent, any two right cosets are equipotent, or any left coset is equipotent with any right coset. So along the same idea, you can also prove that for a subgroup H of a group G, the set of all left cosets, the set of all left cosets of H in G is equipotent with the set of all right cosets of H in G. Okay, so this is again an interesting fact, that suppose you are dealing with left and right cosets both, but the fact is that the number of left cosets of H in G is equal to the number of right cosets of H in G. You will not get more right cosets than left cosets, or more left cosets than right cosets. You will have same number of right cosets and left cosets. So that is an interesting fact we are having. Okay, so how to get this fact? The proof is very simple, just to follow the similar steps that we have considered in the previous cases. But one thing you should be careful about the whenever you are trying to prove this, that suppose you are always keeping in mind that, okay, suppose you are having, so okay, so first, this is the set of all left cosets, okay, of H in G, fine. And suppose this is T, set of all right cosets of H in G, okay. So curly S contains all left cosets of H in G, and curly T contains all right cosets of H in G. Now, naturally, you will have an idea that, okay, so let us correspond each left coset to the corresponding right coset. So that is, so suppose you are always tempting to define this, define a map here that phi of h. So this is a left coset in curly s. So this may be mapped to HA. Okay. So this is a natural inclination to do this fact, but this does not work. If you define this map like this way, it will not work, because what is the fact? Because if you are trying to prove that this map is a, a bijection, in particular this map is 1 1, then you will definitely have, so you are going to take two left cosets AH and BH, and their images are same, and we are trying to prove that the p images are equal, that is AH equal to BH. Okay, so let us take that HA is HB, that is the images are same, that is phi of AH equals to phi of BH, and this implies their images are same, that is their corresponding right cosets, they are equal. But if you do this, then you will find that so it will give you H AB inverse equal to H, right? And this fact implies that A, so what is the fact? The this class is equal to H. What does it mean? What does it mean? This class is equal to H. What does it mean? That means that AB inverse dot E inverse. Here, this H is determined by E identity. So what is a E inverse? E inverse is E, and if you multiply this with AB inverse, then it will be AB inverse. So this belongs to H using the relation, that is AB inverse belongs to H, right? But using this criteria, using this one, you cannot conclude that this does not implies that A is equal to BH, right? Because to make A is equal to BH, you need to have A inverse B belongs to H, this one. So this map does not work good for this case. So what to do? Just take, so let us define, so avoid this one. So let us define phi colon early s to t by just take not the corresponding right coset, just take the right coset determined by A inverse. Okay, that will work. Why? Because again, suppose phi of AH equal to phi of BH, then the will be mapped to HA inverse HB inverse, right? Then what to do? Then it is H A inverse B equals to H, right? So again, using the same thing, the same idea about the equivalence relation. So A inverse B belongs to H. Now you have the criteria of the relation to make two left cosets are equal, right? So this implies AH equal to BH. Okay, so this implies phi is 1 1. And for the onto case, just take, and also for any HB belongs to tau. So what we do? So then B inverse H belongs to S, and so phi of B inverse H equals to H inverse of B inverse. So that is a, so using this, so phi turns out to be an onto map, right? So hence phi is a bijection, which proves that curly S and T are equipotent. That is, have the same cardinality, right? So they have the same cardinality. Okay, fine. So thus we have proved that the set of all left cosets of H in G is equipotent with the set of all right cosets of H in G. That is, the set of all left cosets of H in G have the has the same cardinality as that of the set of all right cosets of H in G. Okay, fine. Now, before going to prove one interesting and important result in basic group theory, and that is due to Lagrange, and it is called the Lagrange's theorem for uh, finite groups. Okay, but before going to prove this one, let us uh, have a look at some examples of cosets. Okay, so yeah, okay. Okay. So let us uh, work out some examples. Uh, Suppose let let us consider uh, the group Z plus. Okay, fine. And suppose that H, the subgroup will be, just take some particular case 6Z. Okay, fine. Okay, then uh, then what are the distinct left cosets of 6Z in Z? So this is a question. How can you generate all those distinct left cosets of 6Z in Z? Now you know that A plus 6Z is a left coset, right? For A belongs to Z. Okay. Now let us start from 0. 0 plus 6Z. What is that? That means it contains 0 plus 6q. Q belongs to Z. That means it contains 6q. The integers of the form 6q, that is the multiples of 6. So it is 6Z. Now what is 1 plus 6Z? That is 1 plus 6q. Okay. That is it contains all those integers whose remainder is 1 whenever you are dividing that integer by 6. So it contains all those integers which has 1 as a remainder in the division with 6, in the division by 6. Okay. Now what is 2 plus 6Z? So it looks like the same thing as above. Sorry, Q belongs to Z. So it contains all those integers having 2 as the remainder in the division by 6. And you can continue this process up to 3 plus 6Z, 4 plus 6Z, 5 plus 6Z, and so on. And now you come to the 6 plus 6Z. What is this coset represents? So it contains all those integers of the form 6 plus 6q. Q belongs to Z. That means since it is 6, so you can take the common. So it is 6q dashed, where q dash belongs to Z, right? So again, it turns out to be the first case, the first coset, 6Z. So 6 plus 6Z, it gives you the first one again. And if you keep moving, 7 plus 6Z, it will be equal to 1 plus 6Z. 8 plus 6Z, it will be 2 plus 6Z, and so on. Right? And why it is so? In terms of the equivalence relation, you can say that since 8 minus 2 is divisible by 6, 7 minus 1 is divisible by 6. Right? Okay? So for that reason, you can say that these classes are equal. And using that fact, so you can say that for any non-negative integer, so for any non-negative integer, small a plus 6Z is one of 6Z, 1 plus 6Z, 2 plus 6Z, 3 plus 6Z, uh, 4 plus 6Z, and 5 plus 6Z, right? So for any non-negative integer, a plus 6Z is one of this one. And now you want to check for the negative integers. Suppose, so let us consider -1 plus 6z. Then what will be happen? Then -1 plus 6z is a set of all those integers of the form this, right? Now you can take this -1 as -6 plus 5, right? And then it will be 5 plus 6 q minus 1. That is, it contains the integers of the form 5 plus 6 q dashed, where q dash belongs to z. This means that it is 5 plus 6z. So thus you have seen that -1 plus 6z coincides with the left coset determined by 5. And another way to view this fact is that a -1 is congruent to 5 mod 6z. Why? As because uh, the minus of -1 plus 5. What is that? This is 6 is divisible by 6. That is, minus of -1 plus 6 belongs to 6z. And using that relation, so you can say that these two are are congruent with respect to mod 6z, and therefore their classes are same, right? Because we know that class A equal to class B if and only if they are related, right? So if you proceed to the next case, that is for -2, then you will going to have, it is 4 plus 6z. -3, you will going to have 3 plus 6z. -4, you will going to have 2 plus 6z. -5 plus 6z, you will going to have 1 plus 6z. And then -6 plus 6z, you will going to have 6z, and so on. Okay, so that means if you take any negative integer, then it will be 1 of 6z, 1 plus 6z, 2 plus 6z, 3 plus 6z, 4 plus 6z, and 5 plus 6z. So -1 plus 6z will be equal to 5 plus 6z. So it will be equal from the opposite order. -2 plus 6z will be equal to this, and this, and this, and this, and this. And then again go to the 5 plus 6z, and then okay, proceed in this way. Yeah. So this means that, so hence this proves that for any integer a belongs to z, a plus 6z is 1 of 6z, 1 plus 6z, 2 plus 6z, 3 plus 6z, 4 plus 6z, 5 plus 6z, right? Which implies that this is the complete list of distinct left cosets of 6z in z plus, right? And in a similar manner, you can also determine the right cosets of 6z in z plus. Now, notably, if you look at this fact closely, then you will see that taking any integer, if you divide it by 6, then the possible remainders are 0, 1, 2, 3, 4, 5. And this helps you to determine these left cosets or right cosets. So generally speaking, if you just okay, so just avoid this case. Forget about the 6z. If you take it any general subgroup in z plus, that is any nz, then any integer, if you divide that one by n, then the possible remainders are 0, 1, 2, 3, 4 up to n minus 1. So that means, so if you uh, adopt this scheme of the proof, then we can easily generalize the fact that the complete list of left cosets of the subgroup nz in the group z plus is nz, 1 plus nz, 2 plus nz, and keep moving, n minus 1 plus nz. These are the all these are all the left cosets of nz in z plus, and similarly, if you consider right cosets, then you will have nz plus 1, nz plus 2, and nz plus n minus 1. Okay, fine. So these are all left cosets of nz in z plus. Okay, fine. Now for the second example, let us consider the group S3, the symmetric group of order 3. That means it has E phi psi square, phi into psi into phi, where E is the identity permutation, phi is the 1 2 cycle, psi is the 1 2 3 cycle, where phi square is identity, psi cube is identity, and phi into psi is not equal to psi into phi. Okay. Now let us consider, now since this element, now let us consider the element phi. Note that, so order of phi is 2, right? Order of phi is 2, which means that H equal to E phi is a subgroup, cyclic subgroup. subgroup of S3. Okay, so H is a subgroup of S3. Okay, so now so now first take the identity. Okay, so let us evaluate the left cosets of H in S3. Okay, so what is EH? So what is EH? So multiply each element of H by E. So it is E and phi, right? So it is H. This is trivial for any case, for any groups. Now phi. What is that? So phi into E is phi and it is phi square. So that means it is again E phi, that is H, right? Psi H. So psi H is psi E, that is psi into phi. Okay. Psi square H, psi square into phi. Okay. 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 Now phi psi H. So it is phi psi and it is phi psi phi. Okay. Psi into phi H. That is psi into phi and it is psi square. So that means it is again psi phi. Right? This one. Okay. These two are same. Okay. Okay. Fine. So ultimately, okay. And now, what is psi square phi? What is psi square phi? Now, since psi cube is identity, so psi square is psi inverse. So psi square phi means psi inverse of phi, right? Okay. Uh, okay. Okay. Uh, okay. So psi inverse of phi, yeah. So that means, that means, so what does it mean? Uh, uh, Okay. So yeah. Okay. Yeah. So what does it equal? To okay. So psi square h. Okay. So psi square h is going to be psi inverse and psi inverse of sorry phi, right? Psi inverse of phi. Okay. Okay. Mm, yeah. So how many cosets left here? So there are. So the first one is h. Okay. The first one is h. The second distinct coset is psi h. This one. Yes, psi h. And um, these two are same. So psi h. Now what about these two? What about these two? I think, yeah. So yeah, this is actually psi inverse of h. Fine. Okay. Now, okay, let me now now uh, yeah. So are these two are equal? These two? Yes. 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 Yeah. Yeah. Mm, Now, okay. What is psi inverse h? Okay, let me check. Okay, so let me check what is psi inverse phi. Now psi is 1 to 3. That means 1 goes to 2, 2 goes to 3, 3 goes to 1. That inverse. And phi is 1 2 3. That is 2 1 3. Okay, so what is the inverse of this? So 2 3 1 1 2 3. So 1 2 3 2 1 3. Then if you multiply this, it will give you. So 1 goes to 2 and 2 goes to 1. 2 goes to 1, 1 goes to 3, 3 goes to 3, 3 goes to 2. Okay, fine. So it is 2 3. Fine. And also, uh, yeah, this is 2 3. Yes. And psi inverse is what is that? So it is 1 2 3 means so 1 goes to 3, 2 goes to 1, and 3 goes to 2. That means So it is 1, yeah, 1 3 2. Yes. So psi inverse is 1 3 2 and psi inverse phi is 2 3. Fine. Now let us calculate this one, phi psi and phi psi phi. So what is phi psi? So 1 2 3 2 1 3, and it is 1 2 3 2 3 1. So this is 1 goes to 2 and 2 goes to 1, 2 goes to 3, 3 goes to 3, 3 goes to 1, 1 goes to 2. So it is 2 3. Yes, fine. Fine. So phi psi is equal to psi inverse phi. Okay. And also we're going to evaluate this one, 1 2 3 2 1 3, and 1 2 3 2 3 1, 1 2 3 2 1 3. So if you calculate this, so you will have, so 1 goes to 2, and sorry, 1 goes to 2, 2 goes to 3, and 3 goes to 3. So 1 goes to 3, 2 goes to 1, here 1 goes to 2, and 2 goes to 1. So 2 goes to 1, 3 goes to 3, 3 goes to 1, 1 goes to 2. Okay. So what is that? So this is actually 1 3 2 cycle. That means it equals with psi inverse. Okay. Fine. So hence, so these two cosets are same. These two cosets are same. Okay. Psi inverse, psi square h and phi psi h. So therefore, we have only three distinct left cosets of H in S3, which are, say, H, and the second one is psi H, and third one is phi psi H. Psi H, and third one is psi square H. Okay. So this is the complete list of subgroups. Okay. Now I am going to give you an exercise now, that now suppose that we consider another subgroup, another cyclic subgroup in S3, which is N. What is N? N is E psi psi square. Now evaluate, find out the distinct left cosets. Just check it out of left cosets of N in S3. I am giving you 5 minutes. I would like to make here that even though the number of left cosets of a subgroup in a group G is equal to the number of right cosets of H in G, but it should be noted that a left coset, particularly individually, may not be equal to right coset, uh, yeah, may not be equal to a right coset, and a right coset may not be equal to a left coset. Okay. For example, in the previous case, so if you look at this, where we have done, yeah, okay, fine, psi h. If you look at this psi h, then so for example, in the previous case, in the previous instance for S3, you will find out one left coset which is not equal to any right coset of H. What is H? E5 in S3. Okay, so this can be this will be evident from the fact that if you find out the right cosets also, we have already deduced these are the left cosets, and if you find out the distinct right cosets, then you will see that this or this left coset will not be equal to any right coset. Okay, fine. So yeah, okay. So I am going to close this session with this problem. What is the problem? That let us find out let us consider the group, suppose Z24 plus. Okay, so the first question is compute all subgroups of Z24 plus and find out their cosets. Okay, find out their cosets. Okay, because this example will give you some interesting fact. So that is why I am giving this problem here. So I would like to close this session here.